We did a couple of examples. I want to do a bit more, okay? Before we begin the new section. So today the class is gonna be very, very heavy on algebra. So we're gonna be doing a lot of, it's basically college algebra, or if you want pre-calculus stuff, that we're gonna be doing once we start section 3.4, okay? But still, I'd like to do a couple more examples on the trigonometric substitution part, and then we move on. Okay, so we did A and B, so let's do a couple more examples. Okay, so evaluate. And let's do similar integral than the last one that we did last time, but as I mentioned, I'm gonna put now different limits just to see how the problem will change. So last time we did the same integral, but it was from square root of 3 to 2. Okay, now I'm changing the limits. I'm making them negative. All right, so we're gonna do this one, and then we're gonna do two more. But the substitution that we do here is very similar to what we did last time. So I'm gonna go ahead and begin the process. So I'm recording, right? Yes. Okay, so let's draw our triangle from here. What's the hypotenuse of this triangle? So let's say that this is theta, so the hypotenuse is x, and then one of the legs is gonna be square root of 3, right? So I'm gonna use this one, and then the other leg is gonna be the square root of x squared minus 3. Okay, so I wanna get a substitution for x, so in this case I'll be using cosine. So cosine of theta is square root of 3 over x. This immediately tells me that theta equals inverse cosine of square root of 3 over x, okay? And if you prefer, because really our x is gonna be secant, right? Square root of 3 secant of theta, you could also write here, if you prefer, inverse secant of x over square root of 3. You know, it doesn't really matter. Remember, secant is 1 over cosine, so if you use a cosine, I prefer to use cosine to look at the angle because it's, I don't know, more friendly function to look at. But if you use inverse secant, that's okay, you just need to flip it, okay? Because cosine and secant, they are inverse of, I mean, they are reciprocal of each other. Anyways, I'm gonna go with the cosine. All right, so at this point, let's decide what quadrant our angle is. So remember, theta equals inverse cosine of square root of 3 over x. The range of inverse cosine is quadrant 1, quadrant 2. It's the same range as the inverse secant. So this will give me an angle in quadrant 1, provided that the argument, the stopping side, is positive. This depends on x, right? If the stopping side is negative, then we're gonna get an angle in quadrant 2. That's where cosine is negative, okay? So question, square root of 3 over x, what is it? Is it positive or negative in this problem? So look at this. Is this positive or negative? Negative. It's negative. Why? Very good. So remember, we are integrating, you have to look at, for one of this question, you need to look at the interval of integration. We are integrating from negative 2 to negative square root of 3. So it means x is between those two numbers. So x is negative. Does that make sense? So this right here is less than 0, since x is between negative 2 and negative square root of 3. So that tells me that theta is in quadrant 2. Do you understand this? Okay, so whatever we do from now on, let's keep in mind that.
So
yes.
For inverse cosine, it's negative in quadrant 2 and positive in quadrant 1?
Yes. Okay. Yeah, so remember, cosine, in quadrant 1, everybody's positive. And in quadrant 2, sine and cosecant are the only ones that are positive. Everybody else is negative in quadrant 2.
Right. So then,
but the range of inverse cosine is quadrant 1, quadrant 2 only. So which one is it? It depends on what you're doing the inverse cosine of. If it's something positive, you will get an angle in quadrant 1. If it's something negative, you're going to get an angle in quadrant 2. Okay? And here it's negative because of the limits of integration. Okay, let's see. Let me quickly check. Okay, looks like I did get an email. No, I didn't. So, Corina, I haven't gotten any email from you. Okay, so yeah, but she said that she sent the email. Still don't get it. So you see, it's not here. It should be there. Oh, it's going to my junk email. I'm glad that I checked. Interesting. But you see, it isn't why? Okay, I know where to find it. So when I get to the office, I'm gonna. Oh, and here it is again. Are you using another email address? Because it says external. Maybe because you're using. Oh, you're using a Gmail account, but it shouldn't be. Okay. Anyways, I will put you on the white list because right now you are on the list that it will just go to the junk folder. Okay. So don't worry, and I know where to find the email now. So whenever you send me another email, it should not go to the junk folder anymore. Okay, so I will reply once I get to the office. Okay, so let's see. Where are we? Okay, so we have our substitution, x equals square root of 3 secant of theta, using the triangle, and it's important to know in what quadrant theta is. So in our case, theta is in quadrant. Okay, that's what we have so far. Okay, so what this means is that I already have a substitution for this guy. Now we need to know what to do with this guy, dx. Now it's pretty easy. Once you have x, just take derivative and you're gonna figure out your dx, right? So dx is gonna be square root of 3. Derivative of secant is secant tangent d theta. That's our dx. Okay. So I already have a substitution for dx, and now we just need a substitution for this whole thing. Okay, the radical in the top. Once again, we can go to the triangle and do it. So you always want to use the side with the square root of 3 to help you out, the side with the number. So in this case, it will be opposite adjacent, so it should be using tangent, right? The function tangent. So tangent of theta is going to be equal to square and opposite over adjacent. Now at this point, we can actually make an observation. What's the sign of the right-hand side in this expression? Is it positive or negative? The right-hand side. Look at the sign of the, look at what I have on the right-hand side. Is that a positive or a negative expression? The right-hand side, what I have written right now.
Right now it's positive.
Does everybody see that it's positive? Square root is always positive. So the top is a square root, so that's positive. The bottom is square root, that's positive. So that fraction is positive. Do you understand this? Now, where is our angle? And what do we know about tangent in quadrant 2? Do you understand this? It's negative. Therefore, it's our job to manually do this. Put a minus there. Because our angle is in quadrant 2, so we need to get a negative tangent. Do you understand this? That's why it's very important, once you make a substitution, you need to have clear in what quadrant your angle is. Because whenever you write something like this, you have to make sure that you're consistent, okay? If you are writing the tangent of theta equals this expression using the triangle, you need to understand that you need to check the sign. In this case, we're expecting something negative, but we had something positive, so it's our job to put the minus. Are we okay with this? Mm-hmm. All right. So after we do this, now we can solve for the square root. So that means square root of x squared minus 3 equals negative square root of 3 times tangent. Questions? So now I'm going to put everything back to my integral and let's solve. All right, so now we make our substitution. So the square root on top becomes negative square root of 3 times tangent. The x in the bottom was the square root of 3 times secant. And my dx was the square root of 3 secant tangent d theta. And now let's change the limits of integration, okay? So let's see, when x equals negative 2, so let me do it here, changing the limits. So when x equals -2, then theta equals inverse cosine of negative square root of 3/2, right? When x is -2, then theta is going to be, just plugging in here in our substitution, the inverse cosine of negative square root of 3/2. So what is this? We know we are expecting an angle in quadrant 2, right? What is this angle? What angle? Let's see. Let's think about the answer in quadrant 1, and then we change it to quadrant 2 using the reduction formula. So in quadrant 1, what angle do you know whose cosine is square root of 3/2? So ignore the minus for now. What angle do you know whose cosine is square root of 3/2? Remember, is it 30 or 60? Which one is it? Or 45? Which one is it? It's 30 degrees, pi over 6. Cosine of 60 is a half. Okay? You need to know these values. I mean, if you don't remember, just use your calculator. You can hit inverse cosine. It's a button that says inverse cosine. Use it. Okay. So, the reference angle of this, remember, this is in quadrant 2. So, the quadrant 1 version, which is without the minus, will be pi over 3. That's it. Pi over 6. That's a reference angle. In quadrant 2, it's going to be pi minus pi over 6. Do you remember how to find this, or should I explain this? Should I explain this? Okay, so okay, are you aware of the reduction formulas in each of the quadrants? Let me explain what this is. Okay, so you don't have to memorize them, you just need to understand what's going on, okay? So our angle is an angle that's going to be here in quadrant 2. We know our theta is in quadrant 2, so we know that theta is going to be somewhere like, right? The terminal side is going to be in quadrant 2. This is what we want to figure out. Now, when every angle always has what we call a reference angle. What's a reference angle of an angle? It's always an acute angle. It's always between 0 and 90. And you figure it out from the picture by looking at the acute angle made between the terminal side of your angle and the x-axis. So our angle is theta. The terminal side is this guy. Therefore, the reference angle is this one. Let's call it alpha. Okay? Because the reference angle is always the angle, the acute angle made between the terminal side and the x-axis. Do you understand this? So now by looking at this picture, you can easily figure out the relationship between alpha and theta. This is the quadrant 2 situation. By quadrant 3, you have another picture, you have another relation. So what's the relationship from this picture between alpha and theta? Exactly. Or alpha plus theta is pi, right? Let's talk in radians because this thing is always in radians, right? So here what we see is that if you do alpha plus theta, you're going to get pi, or 180 degrees, okay? So of course, if you know one of them, then you know the other one. The point is that we can easily figure out alpha, and then once you know alpha, then you can easily find theta. So from here it follows that theta is pi minus alpha. So there is also a relationship between an angle and its reference angle, and as you learned back in trigonometry, the point is that if you ignore the sign, so if you take absolute value, they have the same trigonometric value. So the sine of an angle and the sine of its reference angle are the same in absolute value. It's just that the original angle could be positive or negative depending on the quadrant. The reference angle is in quadrant 1, so it's always positive, okay, whenever you do sine, cosine, or any function. So, but the point is that if you know already the reference angle, and I want to know the cosine of theta, for example, I could do cosine of alpha, but then I have to make it negative. So let's say that alpha is pi over 6. I want to figure out what's cosine of theta. Well, I know that cosine of pi over 6. If alpha is pi over 6, cosine of pi over 6 square root of 3/2. So cosine of theta will be negative square root of 3/2 because it's in quadrant 2. I mean, the cosine is expected to be negative here. Do you understand this? So we always figure out the reference angle, we work with the reference angle, and then you translate your answer back to the original angle if you need to, by using this reduction formula, okay? Which is what's happening here. So if I want to calculate the inverse cosine of negative square root of 3/2, what I can do is ignore the minus. That means I'm going to be getting an answer in quadrant 1, meaning I will be getting my alpha instead of theta. You do it, you get pi over 6, right? But that's not what I want. I want theta, which is the quadrant 2 version. So by looking at this formula, my answer is pi minus pi over 6. Because in this case, in this concrete example, alpha equals inverse cosine of square root of 3 over 2. The positive version, just ignore the negative. Okay? This will give you the answer in quadrant 1, which is your pi over 6. Our answer is pi minus pi over 6. Do you understand this? Okay. So this is then 5 pi over 6. So when x is negative 2, theta is 5 pi over 6. So that means we put a 5 pi over 6 down here. And then similarly, when x is negative square root of 3, so when x is negative square root of 3, then theta is the inverse cosine of negative 1, right? Because you get the square root of 3 over square root of 3. So remember, I'm plugging in here, okay? So if you put negative square root of 3 for x, then you get negative 1 here, your fraction. And you get this, and what is this? So this is pi, right? So this is in none of the quadrants, so you don't have to worry about this reference angle business, because this is a quadrantal angle. So when x is negative square root of 3, theta is pi. That's my upper limit. So now that we have the new limits of integration, we don't have any reason to go back to x. Okay, so when we compute the integral, we just compute it completely. All right, so let's finish this. Any questions before I move on? Are we okay? All right, so some simplifications happen here. These two guys cancel, this cancel, this cancel. So we get, I'm gonna put out the negative square root of 3. So we get 5 pi over 6 to pi, and then tangent square d theta. And remember we discussed last time how to do this. You write tangent square as secant square minus 1, and then you can integrate both of those, right? That's a technique when you have an even power of tangent. So we rewrite this as secant square minus 1. And now we can easily integrate. The integral of secant square, that's tangent, integral of 1, that's theta. And then we plug in our limits. So we get negative square root of 3 times. So let's see, when you plug in pi, okay, let me just do it. Tangent of pi minus tangent of 5 pi over 6 minus 5 pi over 6. Okay, so what's tangent of pi? So tangent of pi, that's 0, right? Because sine of pi is 0. So this guy here is 0. So we get negative square root of 3 times. So far I have here a negative pi. Then what's tangent of 5 pi over 6? That's in quadrant 2, right? 5 pi over 6 in quadrant 2, so it's going to be a negative number. Now, the reference angle of 5 pi over 6 is pi over 6. So the tangent of 5 pi over 6 is the same as tangent of pi over 6, but negative. What's tangent of pi over 6? Square root of 3 over 3. Okay? So it will be negative square root of 3 over 3. So negative square root of 3 over 3, and then I'm going to distribute the negative plus 5 pi over 6. And now let's compute. So let's see. So what is this? That's going to be square root of 3 over 3 plus 5 pi over 6 minus pi. Now 5 pi over 6 minus pi, this is negative pi over 6, right? So that's negative square root of 3 times square root of 3 over 3. Actually, I'm going to distribute. So this part right here becomes negative pi over 6. So I'm going to distribute, and we get negative 3 over 3 plus square root of 3 times pi over 6. So we get negative 1 plus square root of 3 pi over 6. Right. Questions? Do you understand this? Okay. I mean, the end is just, plugging in the numbers and computing and so on. The important detail about this example is to realize the importance in figuring out what quadrant or angle is. Because notice how we had to manually put this minus, okay? If you don't put it, then you're gonna do something completely different. And how do you know that? Well, you have to see. You have to keep in mind the quadrant, and then whatever function you are writing, tangent of my angle, I have to make sure that the sign is consistent. If I'm expected to get something positive, make sure it's positive. If it has to be negative, make sure it's negative. If it's not, fix it and put the minus. Okay? Because remember, after all, we are working with a triangle. But if you think about it, this triangle really, this shouldn't be theta. What should be this? To really be fair, what should be this guy? It should be alpha. Right? But we really have, so now that we know this, what we really have is alpha in here.
Why is it alpha?
Just think about it. In what quadrant is theta?
2.
In quadrant 2. And that's an angle that's less than 90. So really, what you have there is alpha. It's just that it's okay to put theta there in the sense that we're just using this for reference to make a substitution. Okay? But what you need to understand is that what we have here really is an alpha, because this is a quadrant 1 picture. Because it kind of contradicts itself. You're showing me a triangle with theta in there, and then you're telling me here that theta is in quadrant 2. What are you talking about? Well, because the triangle that we have there is really this one. This is really a triangle that we have in that picture. That's really a triangle that you have in that picture. Okay? So now you have the full story. But I mean, it's okay to put theta here, but you need to understand that it's really alpha. But then you need to have all of these in mind of the reference angle, and it's adding an extra layer of complication. I don't want you to have that. Just the only thing is that you have to be careful with the sign. That's all. Okay? All right. So if you want, we made the comment here. Because of this, and then above, in the triangle, we really have alpha, which is the reference angle of theta. Okay? And then let's see. Let me show you the proper way, okay? Even though I think it's easier if you do it like this, that way you don't have to worry about too many things. But if we do it the proper way, let me put it here. So, proper way. So we begin with our triangle, right? Putting theta here because if you don't know what's going on, then we do it in an innocent way. So it's our x, it's the square root of 3, everything is fine. Then we start solving and we say, okay, cosine of theta, square root of 3 over x, and then this tells me that my theta is gonna be the inverse cosine of square root of 3 over x. And it turns out, because of the problem, remember our exercise came with the condition that x was between -2 and negative square root of 3. Because those were our limits of integration, okay? So when you put that condition in place, then we realize that, oh, wait a minute, this is in quadrant 2, okay? So we need to work with alpha. Yes?
So if this was an indefinite integral, right, and we didn't have those limits to tell us it was negative, then we just wouldn't put a negative.
Exactly, we don't worry about that. Exactly. So then you see, so if it's indefinite, yeah, you don't worry about that. Right. But because you have the limits, you have to worry about it. Right. Yeah. So in this case, we need to work. We need to work with alpha instead. In other words, here alpha is the reference angle. Okay, but that's okay. I'm still gonna be using my theta, but I have to then come back here and put alpha. Okay. Yes, I'm gonna put alpha, but then you see, then I have to do this. Because our x is negative, so it doesn't really make sense to have x here. This is a hypotenuse of a triangle. What do you mean by saying, oh, the hypotenuse is negative 2? What is that? That doesn't make sense. The hypotenuse is 2, right? Because it's the length of a triangle. So if we're trying to do this the proper way, then we need to stick an absolute value here. The point is that we need to remove that absolute value, okay? All right, so by doing this, we already have our x, so that's not really a problem. Now we're gonna check for consistency. So according to the triangle, let me show you I'm gonna do the triangle here. So according to a triangle, really what we have is that absolute value of x equals the square root of 3 times secant of alpha, right? That's what my triangle tells me. My absolute value of x equals square root of 3 times secant of alpha. Now, what do we know about secant of alpha? Secant of alpha is the same thing as secant of theta. It's just that this one is positive and secant of theta is negative because we're in quadrant 2. Theta is in quadrant 2. So if I replace this by secant of theta, I have to put a negative. But that negative, then I can translate it over here. Okay? And when x is negative, what's absolute value of x? Actually, let me do that. So when because x is negative, absolute value of x is equal to negative x. Right? You have to put the minus in front to make it positive. It's like when you say absolute value of negative 2, well, this is minus 2. Right? So then you can get 2. How do you define the absolute value function? As a function, how do you define this? This was the first piecewise function you defined back in college algebra. This is x as long as x is greater than or equal than 0, and this is the negative x function as long as x is less than 0. That's how you define absolute value. Just think about the picture. This is the picture of the absolute value function, right? These are really two functions. What is this function? This is the function y equal x. What is this function? This is the function y equal negative x. You're just taking a piece of those functions. So, I mean, y equal x is the whole line, but you're only taking y equal x as long as x is greater than or equal than 0. When x is less than 0, you don't look at the red line, you only look at the blue line. Right? That's really what's happening. So, that's why I put the negative x here, because I'm removing the absolute value, but then the minus cancel. The minus cancel, and we get this, which is the same as what we originally had. So there is no problem here. Do you understand this? So you can either have alpha or theta, it doesn't matter, but if you do it properly, you need to have alpha here, but if you put alpha, then you have to put absolute value and you have to deal with all this business. Okay? That's why I'm telling you above. You can put theta, but keep in mind that if your angle is in quadrant 2, you have to be careful. So the sign has to be fixed at some point manually. I'm doing this because, you know, this kind of seems forced. Like, you know, all of a sudden we are putting this minus that, you know, we're kind of forcing this. But the price that we pay if you don't want to force it is that you have to, you know, work a little bit more. Anyways, but let me just show you this. That way I don't have to talk about this anymore. Okay, so that's that. So once you have x, then immediately we already see that those are the same. So then dx is fully justified because all I'm doing now is taking derivative. That's all. So that's not really a problem. So now, the nice thing is about tangent. So if I wanted to calculate tangent now, okay, so if I wanted to calculate the square root, okay, now I can use tangent. But to do it properly, we need to do tangent of alpha, right? So that would be this. To do it properly, that's tangent of alpha is equal to this, and this is okay. My tangent is positive, my alpha is positive, right? And my fraction here is positive. Now, the thing is that our angle is not alpha, our angle is theta, right? So we want to go from tangent to alpha to tangent of theta. Now, what do we know about the relationship between tangent of alpha and tangent of theta? Because alpha and theta, they are reference, you know, alpha is a reference angle of theta. Then we know, so note, we know that tangent of theta is negative tangent of alpha, That's a relationship that that angle and its reference angle have. And why do we know this negative? Because theta is equal to 2. Okay? So now that means I can replace my tangent of alpha by negative tangent of theta. And that's where that negative came from. Because then tangent of theta is just minus this guy. You see? That's really where that negative came from. But you know, if you you know, you can go through all of this if you like every single time, but you know, just now that you saw the truth, it's okay to do this and even to put a theta here, even though it's in quadrant 2, but then just keeping in mind that then you have to manually come here and fix the sign. It's up to you how you want to do it. Okay? Yes.
What if the limits were -2 to positive square root of 3?
Okay, so that's a good question.
Would we just separate to do like -2 to 0, and then a second integral 0 to?
So first of all, if that happens, we haven't discussed those type of integrals yet. That's what we call an improper integral. Okay. And why is this? So what's the problem if you have a -2 to square root of 3? There is something implicitly here that we should be checking all the time, and we have never wondered ourselves if that property is being satisfied or not. We're freely using fundamental theorem of calculus here. Yes? But what's the condition for us to use fundamental theorem of calculus? Function better be continuous. Okay? 0, this function is not continuous at 0. This function is not defined as 0. You see, it has a problem at 0. Right. So if it would have been from -2 to positive square root of 3, you cannot use fundamental theorem of calculus. So what we're saying here doesn't apply to the situation. You understand? So in that case, that's an example we call an improper integral. That's what we're going to learn some sections down the line. There's a limit that you need to take, and there's some work that you need to do before you get to integrate. But then essentially what we do is we will split it from -2 to 0, because when the singularity is in between, when the discontinuity is in between, we split it. We want the discontinuity to be one of the limits. So we will do it from -2 to 0, and then from 0 to positive square root of 3. Okay. -2 to 0, we deal with that in one special way. At some point, this is going to happen, what we're doing right now. And then from 0 to square root of 3, we do it also taking a limit and so on. And what will happen is the positive ratio. So you'll be dealing with a quadrant 1 situation. Okay. So it will be 2 cases, quadrant 2 case and then quadrant 1 case.
Okay. So in that scenario specifically, that the 0 would cause it to be discontinuous because there's x in the denominator.
Yes.
So if there was no x in the denominator and we had -2 to positive square root of 3.
Yes. I will split it. So what I do is I split it from -2 to 0. Because you need to control the things that you need to control the sign of your variable. You need to know your variable is positive or negative. Right. And then to be able to do that, you need to have intervals where the variable is either fully negative or fully positive.
Right. So in that scenario, we wouldn't need the improper integrals that you mentioned. We can do it with what we know right now.
Exactly. Yes.
Okay. We would just separate.
Yes.
Okay.
Yes. It will be from -2 to 0, and then plus from 0 to square root of 3. Right. The first one you deal with it the way we did here, because it will be a quadrant 2 case, blah, blah, blah. And then the second integral will be what we did last time, which is the quadrant 1 case.
Okay, got it.
Yes. Good. All right. Are we okay with this? All right, so let's see. This took more time than I wanted, but that's good, because that way, I think this is the first time I explain this by doing the proper way as well. It's just that I always feel bad when I say, well, look, you have to put a negative here. And, you know, many people say, well, okay, I have to put a negative. That's it. But, you know, you should wonder why. Why are you bringing a negative now that has no business? You know, what is this? You were told not to ask why. Right? So, why?
Why can be a dangerous question in math class.
It is. I mean, as you can see, in this case, it's not that dangerous, but in general, sometimes I would tell you, look, the why is beyond, you know, our scope right now, so I would not even bother. But I think this is something that we can handle, right? This is stuff that you already know. Just need to see how to put it together. Okay, let's do another one. How about this guy? Again, all of this is when you have limits. If you don't have limits, it's a happy day. Okay, so you can just go on and do your technique. Okay, so let's do square root of x squared minus 2x. This one is actually similar to the one above, but there is no denominator, right? Now, what I want to show you here is another strategy, which in this case, remember, to be able to use what we need to have something square minus a number in here. We don't have a minus or plus a number, but here there's an x as well. So what should we do in this case? We need to complete the square. So we don't have something square minus or plus a number, so to be able to do that, we need to complete the square first, okay? Why? I don't like this 2x. That x right there is not good. If we had a 2, that's good, but we have an x in there, that's not good, we need to get rid of that. So in this case, we need to complete the square. So, complete squares. So we have x squared minus 2x. So what do we do to this? We add, so negative 2 divided by 2 is negative 1, squared, that's 1. So we added 1, but then we added, we need to subtract, right? So this becomes x minus 1 squared minus 1. So our integral is the integral of square root of x minus 1 squared minus 1 dx. Did you understand this first step? Now we can proceed as usual, because now we have something squared minus a number. That's good. So now I can draw my triangle. What's the hypotenuse of this triangle? Very good. X minus 1. Then one of the legs is 1, right? And then the other leg is my radical. Now here I'm going to put, for convenience, the original one, just because it's the same, right? It's just like shorter. So I'm just going to write the original one. Do you understand that this is the same as what we have here? They're equal, okay? All right, so now we're good. So let's see, I want a substitution for, let's see, there is no x in here per se, but we still have a dx, right? And to get to dx, we need to figure out what x is, okay? Even if we don't have an x by itself in the integral to substitute, you need to still find it because we need to figure out dx, okay? So to get to dx, we need to know x first. So to find x, I'm going to be using adjacent and hypotenuse. So again, cosine is 1 over x minus 1. So that means x minus 1 is going to be secant, and therefore x is 1 plus secant. Once I know x, I know dx. So dx is going to be secant tangent. So we know dx. Now we need to figure out the radical, and for the radical, I'm going to be using tangent. So tangent of theta equals opposite, well, adjacent, in this case over 1, so the radical is equal to tangent. So remember that this is the dangerous place. If we have limits, this is when you need to make a decision, do I put a minus or not, okay? But we don't have limits, so we don't have to worry about that. We're just manipulating symbols, if you will. That's what we're doing, okay? We're just manipulating symbols. Okay, so we are ready to do the substitution. So the integral becomes, the radical is tangent of theta, and then dx is secant tangent. So our integral is tangent squared times secant. Questions? Did you understand this? Now, this is the painful case, right? So how to solve this? We need to write tangent and secant squared minus 1, distribute the secant, and we're going to get secant cubed minus secant. We know the integral secant, but then secant cubed, you need to do, by parts, right? You have to do integration by parts. We did this last time, so I don't want to repeat the same problem. So I just borrowed that. So you see, last time we were computing that integral. We were computing another integral last time, this one, and that integral ended up after the substitution in the same expression, tangent squared times secant. Okay, so I'm just going to copy that. The only difference is that we have a 1 over a. So if we take out 1 over a from here, we can fix it. So I'm just gonna copy this. Do you understand why I'm copying this? Because I mean we did it last time. Okay, I just don't want to do the same problem again. But understand that this result that I just copied is by multiplying 1 over 8. We need to take it away. Okay, how do we take away 1 over 8?
We define.
Multiply by 8. Or you divide by 1 over 8, which is multiplying by 8. Yeah. So my answer is really this times 8. Okay, so I'm gonna fix it now in the next one. Okay, so it's gonna be equal to, paste it and put it down here. So from last class, but then when you multiply by 8, this comes back to a 2, right? That becomes a 1/2. It was a 1 over 16, but now it's 1/2 because it times 8. Anyways, when you do that integral, that's what you get. Okay, I didn't do it because we did it last time. All right, so now our job is to go back to x, remember, but that's okay. We have a triangle, so we can do it. So let's see, in this case we have 1/2 times, so secant is x minus 1, and tangent is the square root of x squared minus 2x minus 1/2 ln of x minus 1 plus square root of x squared minus 2x. And that's good enough. All right, questions? So the purpose of this example was to show you that sometimes you may need to complete square before you activate this process of the trig substitution, okay? So even if it doesn't appear to be of the form that we previously discussed, you know, something square minus a number or something square plus a number and so on, you can complete square and make it look like that, okay? That's the point. That's what I wanted to illustrate with this example. Questions? And lastly, one more. You may have problems in which you don't even see the radical, even though it's there. That's what I want to show you now. Let's do this integral. So when you see this, you may say, well, I don't really see a radical here, so why is this, you know, why should we think about trigonometric substitution? And really the point is that you don't even need to see the 3/2. If you will, the radical is right here, right? That 2 in the denominator is the square root. It's just that we're cubing now stuff inside, okay? But if you want, you can think of this as this. And then cube, right? And now you see the radical. I'm gonna tell you even more because we're gonna need this for the next stuff that we're gonna do. I'm gonna tell you even more. If you didn't have the 3/2, let's say that, I don't know, that 3/2 was, imagine that it was like this. Let's say this was cube, right? We don't have a 3/2, we have a cube. What can we do here? If we had something like this, we can still play this trick. It's just that, just remember that when you do that, you know, assuming that your quantity is positive, like in this case, square plus 5 is positive. If a is positive, you can always rewrite it as square root of a squared. Do you understand this? Yes? So 4, I can write as 2 squared. That's basically what I'm telling you, okay? So that means that I could rewrite this as square root of x squared plus 5 squared, and then cubing. So that would be square plus 5 to a 6. And then I see my radical. You can use that then to do your trig sub, etc., etc. You understand this? So just keep in mind that you have these tricks, these techniques available, okay, whenever they show up. Anyways, let's go back to the exam. So that's the kind of situation that I'm trying to illustrate.
Yeah.
Okay. Yeah, I'm getting rid of that because it's not really,
Right.
you know, it's exactly the same as what we have above, to not create confusion later. Are we okay? All right. So now that we did this, now we see the radical. So let's go and let's make a substitution. So we draw a triangle. This time, let me draw my triangle over here. The theta, and then what's the hypotenuse in this case?
X squared plus 5.
Is a full radical, right? So that means that one of the legs is x, and the other one is square root of 5. Remember, you have to take square root. Pythagorean theorem. The Pythagorean theorem has stuff squared. So this is one of the legs squared, so the leg is square root of 5. Okay. All right. So now we begin. So tangent of theta. Remember, I'm solving for x now. Why do I want to know x? Because I need to figure out the x. Okay. So opposite adjacent. So that's x over square root of 5. So my substitution is going to be square root of 5 tangent theta. Therefore, dx is square root of 5 secant squared. So I already know what dx is. Now I have to figure out the radical. What function should I use for the radical? I want a substitution for this now. What function should I use? Cosine, right? Cosine or secant. Secant is faster, but let's do cosine. We do whatever comes to our mind first. Remember, adjacent hypotenuse, you should think about cosine. But then, because it's in the denominator, when you solve for the radical, you're going to get square root of 5 over cosine, which is secant. Right? And the radical is square root of 5 times secant. So we are ready. So the integral becomes 1 over, let's see, we have a radical, which is square root of 5 times secant, but then we need to cube this. And then dx, that was square root of 5 times secant squared d theta. Yes? I'm just replacing what we have. So let's see, let's do some simplifications here. So this is going to be, so square root of 5 cubed is the same thing as saying square root of 5 times square root of 5 times square root of 5, right? 3 times. The first 2 times, that's just a 5. So that's 5 square root of 5. So that would be 5 square root of 5 secant cube. So now this square root of 5 is gone with this one, and we get a 5 in the denominator. And then the secant squared is gone with 2 secants from the bottom. So we're going to get 1 over 5 times the integral of 1 over secant. So this turns out to be a very easy integral, right? So what's 1 over secant? Just cosine. What's the integral of cosine? It's just sine. And now we need to go back to x. Who can tell me what's the answer in terms of x? 1 over 5 times. Okay, Daniel, don't worry. Yeah, of course. X over square root of x squared plus 5. All right, questions? Any question? Do you understand what we did here? Okay. So, Jason, you have a question?
Yes, Professor. At the top of this, where you have 1 square root 5 secant theta, 1 over square root 5 secant theta cubed times square root 5 secant squared.
Yes.
Could you can't simplify that by just kind of canceling that square root 5 secant squared and 2? Like, can you separate the cube on the bottom of that fraction?
Yes.
Because then you wouldn't get 1 over 5. Wouldn't you get 1 over square root 5?
Okay. So there is a product, right? So let's talk about this first. So that means square root of 5 cubed, right?
Right.
So square root of 5 cubed is square root of 5 times square root of 5 times square root of 5. Agree?
Yeah.
Okay. The first 2 times that you multiply square root of 5, that's a 5.
Mm-hmm. And then
So there is another square root of 5 left over. So that's why you see the 5 square root of 5 in here. This one. I haven't simplified anything yet. I'm just rewriting the expression. Do you see that?
Yeah.
Okay. In other words, square root of 5 cubed is the same as 5 times square root of 5. And then the secant cube is secant cube. So now I cancel. I cancel the square root of 5 in the top with the square root of 5 in the bottom. And the secant square on top cancels with 2 of the secants in the bottom, and there's 1 secant remaining.
Okay. Yeah, I just realized where I was wrong. Okay. Thank you, Professor.
Okay, no problem. All right. Are we okay? All right. So again, you have the homework, and the homework you have more problems. Okay. So, but now this is pretty much what you do. If you do the triangle, you don't. The triangle tells you exactly what's gonna happen. As long as you understand how to draw a triangle, you should be fine. Okay.